Okay. Here we go. We're not going to do much by the way of examples today. We're going to talk about some new ideas for the most part. But they are important ideas. So last time, we saw the continuous functions, the quintessential, or we talk about elementary continuous functions. And these were the guys that were continuous on their domains. This included the polynomials, the rationals, the rational function. I thought the word functions. Radical functions. Of course, the exponential functions. The logarithmic functions. And the trig functions. These were the functions we saw were continuous on their domain, meaning at any point where they are defined, they are also continuous there. As we said, this is actually not a very typical thing. It's actually a very strange thing in general. There are many functions for which this is not true. But these functions are the nice functions. They're mostly the functions we're going to be dealing with. And if you have these functions and combinations of these functions via multiplication, division, addition, and subtraction, etc., these are called the elementary functions. So in Calc 2 you might hear someone says, oh, this has no answer in the elementary functions. And what they mean by that is we can't write an answer that uses these functions in them. So these are the very elementary functions. Pay attention. Okay. What I also want to talk about now is some more facts about continuous functions. These are very important facts. In fact, I'm going to state them as theorems. So let's talk about theorem 1. And this is a theorem that says basically combinations of continuous functions are also continuous. So let's say f and g are continuous at x equals a, and c is a constant, then the following are also continuous. At x equals a. So given two continuous functions and a constant, it is automatically true that a constant times the function will also be a continuous function. If I add two continuous functions or I subtract two continuous functions, the result will also be a continuous function. If I multiply two continuous functions, the result is also a continuous function. If I divide two continuous functions, the result is also a continuous function provided that we are not divided by 0. So we know these as the quintessential continuous functions, but it turns out any combination of them that we can do with addition, multiplication, subtraction, or division will also be continuous. So if I take a polynomial and add it to a radical function, we're on the domain of that function, it will be continuous. Or if I multiply any of these two types, etc. Right? This continuity is maintained by these operations. Now you might notice that the composition is missing here. Well, we deal with that in a second theorem. Let's call this theorem 2 here, just with our own numbering. Suppose f is defined at e, and we have that the limit as x approaches a of g is b, then limit as x approaches a of f of g of x is going to be f of b. So that's this second theorem to deal with composition. You can say a little bit more about the composition here. Let's talk about theorem 3. And this basically says if f is defined at g of a and g is continuous at x equals a, then f of g of x is continuous at x equals a. So these are just some theorems about continuous functions, how they relate to scalar multiplication, regular multiplication, addition, subtraction, and division. And this is how they would relate to composition. Right? So these terms are very important. Right? So these are the functions we'll be dealing with, but we can also mix and match them in various ways, and we will not lose continuity by doing this. So that's very important to know. Right? And in these theorems is kind of why in the last class when we were talking about where something is defined, if it was, for example, a piecewise function, and it was like whatever down here, blah, 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 we could have determined that this didn't have a problem because the sign didn't have a problem and the x didn't have a problem unless you're at 0. We could look at the pieces of this function separately because of this theorem. Right? So last time we were doing that, we could really only do that because this theorem exists. And this isn't a trivial theorem. It's something that you had to prove using the precise definition of a limit, which we'll start talking about later. So I'm not going to prove it, I'm just going to state it. You should just know, given continuous functions, all these will follow. Another consequence here Theorem 2 leads to an important idea that we'll use at least a few times, but it's something that people use a lot in general. And that is the idea that limits pass through continuous functions. Right? That's an important idea. What you could kind of look at this theorem as saying is that you could take the limit, move it past the f, right, and actually apply the limit to the g inside the f function. It turns out this is something you can do with continuous functions in general. So for example, if we have, say, the limit as x approaches a of sine of some function, as long as that limit exists, it will be equal to sine of the limit of the function. Right? I can kind of move the limit past the continuous function and operate directly on its input. Right? This in particular could happen for exponentials, for example. So if I want to find the limit of e to some blah blah blah, it turns out I can move the limit past the e and apply it directly to the power. So once these limits actually exist, both sides of this equation will give us the same result. And this is the idea that limits can pass through continuous functions. And the definition of being continuous also kind of suggested that, where we're like, so you can also look at it from that angle, where we said a function was continuous means that limit as x approaches a of f of x is equal to f of a. Well, technically you could look at that this way. This just means we pass the limit inside. But the limit as x approaches a of x is a. So you can think of continuous functions in this way. You can literally move limits in and out of them. You can factor limits in and out of continuous functions. You can't do this in general. You can't do that for functions in general, but for continuous functions you can. And so that's a useful algebraic trick that might come in handy sometimes. So that's definitely important to know. What else do I want to tell you guys? Okay, so all those guys are continuing, so it's continuing, Then passive continuous function. Oh, I put a VTW here, by the way. So I've mentioned the number e before, and I told you about the e to the x, the most important function in calculus and math. And so now with the language of limits, I can actually define this specifically for you. The number e is equal to the limit as n approaches infinity, 1 plus 1 over n to the n. And so that's just something you should know now. So that came from, as I was suggesting, the compound interest formula. You might remember that formula says that P is the principal, is the original amount that you deposit into an account, earning R interest rate, and N is the number of times you're compounding it, T is the number of years that you are applying the interest for. And so we looked at the question of setting P equals to $1, setting R equals 100% interest rate, which is 1, setting T equals 1 year, and then letting N go to infinity. Imagine that you compounded such an amount an infinite number of times within 1 year. What would the result be? Well, it would be E. Notice that what we do here is plug in P equals 1, R equals 1, T equals 1, and then let N approach infinity, which before we never had a way to express this idea, but now we do. So now I can say let N approach infinity of this expression, and you get the number E. That's kind of where it came up. So we have that. So that's a very important way. You should know that E is this expression. There's actually another way to write this down. So that's the expression as a limit at infinity. It is equivalent to the following. You could write it as a limit approaching 0 by just taking reciprocals. So that's another way to notice it. Notice that. And if you wanted to define the function e to the x via a limit, you could also do that. You just replace the interest rate with x. So it's 1 plus x over n. A very nice way to express e is as an infinite sum. So e is going to be the summation and goes from 0 to infinity of this expression here, which you can think of it as an infinite sum. This is going to be 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x. You add up an infinite number of terms, that's e to the x, and that will also be e to the x. This is called the power series or the Maclaurin series at e to the x. You'll see that in Calc 2. But that's by far the most useful way to think of e to the x. But for us in calculus, you really want to think of e in this way, and it's going to pop up every now and then. And just so it turns out that that particular expression seems to pop up all over the place, and which is why e to the x is a very important number. So I just wanted to make sure you knew what e was as this expression. It's important that you remember these. Right? So now this is now, as a calculus student, this is one of the formulas that you should always have in your mind at all times. Kind of like how you all kind of know the difference of squares formula. Whenever you see a squared minus b squared, it's a knee-jerk reaction to think a minus b times a plus b. Now whenever you think of the number e, which if you're a calculus student should be often, that should be something that you immediately kind of think about it. So when you hear e to the x, you should imagine the picture in your head. It's just an exponential function looking like that passing through 1. You should also think of this definition. So I kind of discussed E, but I never really defined it specifically for you because we didn't have the knowledge of limits yet. But now that we do, that's it. That's E. That's how you actually compute it. So people invented E by computing this limit, and that came up by thinking about this question. What would happen if $1 is infinitely compounded at a 100% interest rate over a year? How much money would you have? E dollars is what you would have. Okay. Now we're going to look at an important consequence of continuity. This is called, very big in theorem, very important theorem, it's called the intermediate value theorem. Might write IVT for short. It's a very important theorem, one of the big theorems of the semester. We're not going to prove it because it requires you to have knowledge of things like the completeness axis for the real numbers, and we're not going there. But it is one of those big theorems. It's a theorem that as a Calc 1 student, people expect you to know. Just like how if you tell someone, I did Calc 1, they'll say, okay, so he knows how to differentiate x squared, he knows what a derivative is, he knows the fundamental theorem of calculus, he knows the intermediate value theorem. This will be an assumption that you know this thing. It's a very important theorem. And it's a theorem that is true only in the case of continuous functions. So the theorem says the following. Assume or suppose f of x is continuous on the closed interval AB, right? Closed interval. It's important you pay attention to the intervals. We'll have a couple of theorems where we're talking about a certain interval. Okay. So if something is continuous on the closed interval AB, and let's say f of a is less than or equal to n or less than b. Let's say there's a number that is strictly between the y values f of a and f of b. So there's a y value that's in between these two y values. The order doesn't necessarily matter. You could have the f of b being the less and the f of a being the smaller, or vice versa. Right? The point is there is some value, there is some y value in between the y value of the function at the endpoints. Then, so now here's the conclusion. If you know a function is continuous and you know that this is true, you can make a certain conclusion. Does anyone remember what that conclusion is? Anyone did intermediate value theorem in calculus before? I think from high school calculus. You guys remember what you can conclude? Yeah?
Maybe the value of x will be between a and b.
The value of x is between a and b? No, the value of x such that what?
So I don't know how to put it.
There is, or there exists, a c in the open interval AB such that, so that's some x value, some input value. What is the result? Do you remember? Such that f of c will give you that output n. This is called the intermediate value theorem. Basically, it's a theorem that says a continuous function will hit all intermediate y values. If I know the y values at the end points, then that continuous function will attain every single y value in between those 2 points. So this is basically a rule that says the following. Okay. So let's say you have a function doing whatever it wants to do. Function doing as it do. Right? And you know, here's your f of a, and here's your f of b. So these are two y values on the y-axis. The intermediate value theorem says, as long as your function is continuous on that closed interval, there are no holes, there are no gaps, there are no jumps, there's no any craziness going on, but your function moves continuously between these 2 points. For any value, any intermediate y value you pick, it doesn't matter who you pick, if I can pick some at random here, there will be an x value in between a and b, such that the output of the function will give you that. To illustrate at this point, it'll be roughly here. So if you have 2 y values, any intermediate y value will be an output of your function at some point inside that interval. There will be an input such that when you take f of that input, it will hit that intermediate y value, whatever you pick, and that's called the intermediate value theorem. It's a very important theorem. We use it to prove a lot of other important theorems. So it's probably the first most important theorem of the course. And that's basically it. A continuous function will hit all intermediate y values on a closed interval. So you are guaranteed to be able to find such a position. Now to prove that is a little bit subtle, so we're not going to do it, but you should just know what the theorem says and know how to use it, in particular with a problem like this, which is a very typical problem for a Calc 1 class. Show that the equation x plus 3x plus 5x plus 3 equals 0 has at least one solution on the interval -1. Another way of saying that is to say, suppose f of x is equal to x cubed plus 5x plus 3. Show that f of x has at least one root in this interval. A root is just an input value that gives you an output of 0. It's the 0 of a function. Okay. So, a very typical kind of problem, and basically intermediate value theorem, a problem like that is guaranteed to come on your test, and basically I'll ask a question something like, I'll ask you this, and then I'll ask you, how do you know that that will be the answer? And you're supposed to respond, it's continuous. I'm telling you, that's coming up. Right? So I'm going to say, show that this has an equation. It has a solution. You're going to write down and show how it has a solution. Then I'm going to ask you, how do you know? And then you're like, it's continuous. So the intermediate value theorem tells me so. Okay. And that's pretty much the script. Okay. So it's a very common type of problem. And so now we're going to solve this. Now you might think of solving this by more elementary means. Back in algebra class you learned something called the rational roots theorem. So you probably would have tried that. And so you probably try to do the test points, because you'll probably expect that you have to do a long division or something, so you'll do test points. Since the coefficient here is 1 and that's 3, you test the points plus or minus 1, plus or minus 3. But notice that when you plug these in here, you don't get 0. So now you're stuck. Okay, now algebra has failed us. Okay. So what do? We can still know that this thing has a solution, and once we're specified the interval, it's on a closed interval, we can actually know that the solution will exist by the intermediate value theorem. So here's how we do it. So first you would note f of x equals x cubed plus 5x plus 3 is continuous on -1 equals 0. Why? How do you know that's continuous? Yes? Because it's a polynomial. Maybe I should write that out. I'd expect you to say that. Since f is a polynomial. So in other words, polynomials are continuous on the entire real line, therefore it's definitely continuous on this small interval that you've given. Okay? So that's the first thing you're going to notice. You need to note, I do have continuity here. Okay? So this expression is that of a continuous function. This means, by the intermediate value theorem, we can say, or maybe I shouldn't say by the intermediate value theorem yet, just make it sort of a punchline. Let's do it that way. Also note, let's evaluate the function at the endpoints. What is f of minus 1? What is f of minus 1 here? Yeah? Minus 3. What is f of 0? Positive 3. Okay? So this function hits minus 3 and positive 3, and I want to be able to conclude that it will hit 0. Right? Well, how would I do that? So now you can say, by the intermediate value theorem, there exists some number in the open interval. That backwards E is a symbol that means there exists, or there is at least one. There exists some number in the open interval such that f of c equals 0, i.e. c is the solution to the equation, or c is a solution. In general, they might be more than one, but we know there's at least one by the intermediate value theorem to the equation sk plus 3x plus sk plus 5x plus 3 0. And that would be your conclusion. And all your answers are pretty much going to look like that. So a problem like this, show that this equation has some solution in this interval. You are going to note where that solution is continuous, and you better be able to justify that it's continuous on the given interval. This one is easy. It's a polynomial. They're continuous everywhere, so it's definitely continuous over there. So we know we have continuity. We plug in the two endpoints. It hits a y value of minus 3 and a y value of 3. So basically we have a situation where at minus 1, our function is at minus 3. At 0, our function is at positive 3. Right? It's continuous, meaning there's no break, no gap, so whatever it's doing, there must come a point where it's going to cross that x-axis. Right? And I know that point must exist on the function because it's continuous. There's going to be no hole or no gap. To move from negative 3 to positive 3, it has to pass through 0. Right? It has to hit every intermediate value, particularly in this case it'll hit 0. So I know there's at least one time when it will do that by the intermediate value. Any questions on this? Now this in particular is a very important thing to be able to talk about. I know a lot of students, a lot of people in general, I guess, not even just students, they think of math as it's always this exact thing. You always need to be able to tell the answer exactly, and you should be able to write it down nicely. Sometimes that is not possible. Sometimes an equation can be very difficult to get to the answer. Sometimes an equation might not even have a very nice way, or we are not aware of a very nice way to get to the answer. But for various situations, solving certain equations would be a very important thing to be able to do. But if you can't solve it exactly, I mean, technically this isn't so bad. There's actually a formula to solve for a general cubic. But once the power is 5 or greater, such a formula doesn't exist. So sometimes it's impossible to actually solve an equation. So what we do instead is we try to approximate a solution. So we might start to throw out some intervals and try to see, is there a solution there? And the intermediate value theorem can do the check for us. And then if our error here is just not satisfactory, we might start closing it in. What about on minus a half to 0? Is it there? And we can do the check. And then we can start closing in. What about minus a quarter to minus 1 over 100 is the solution in that window? And you can keep applying intermediate value theorem. So you can, in theory, write a program, or there are programs that do this, that it will just keep decreasing the window and keep checking intermediate value theorem every step of the way until you get within a window that's tolerable for you. And a lot of times that is perfectly fine. You never get to the actual answer, but you don't have to. Because in reality, a lot of times getting to the actual answer, even if you could, it would essentially be useless, right? So let's say you're trying to build a house and you need to cut a board exactly pi units long for this house, okay? So you have to cut it pi units long. Now pi is an irrational number, has an infinite non-repeating decimal. No one has ever computed all of pi. No one can ever compute pi. No machine can ever compute pi. So you put it in a machine and tell it, cut this thing pi units long. It's not going to cut it pi units long. It's going to cut it some approximation of pi units long, right? It can only be accurate up to a certain number of decimal places. You never actually ever need to know what pi is because it's not something that can ever actually be computed, right? So a lot of times when you're using pi, you plug into a calculator, it's not pi, it's just the first few digits of pi, right? Even your TI-89 uses maybe 15 decimal places when you plug in pi. Right? So sometimes getting to the actual answer or using exact answers isn't really possible, isn't really a thing, but knowing how to approximate something and being able to get a window of where the answer is a very valuable thing to do. And classes like numerical analysis go into this kind of thing all the time. You learn approximation techniques for things because they're super important. And so in some cases, in the continuous case, the intermediate value theorem can help a lot with approximations. It helps with a lot of other things too, but this is one way in which a Calc 1 student should be expected to apply the intermediate value theorem. So there's that. So those are some important ideas. So far, takeaway from this class, intermediate value theorem. You need to know it very well, you need to memorize it, know it by heart, and be able to apply it. You need to know what E is as a limit. You need to know the fact that having two continuous functions, adding them, subtracting them, multiplying them, dividing them yields a continuous function. You need to understand that limits can pass through continuous functions. Those are the takeaways so far. Okay. And that ends this current section. We are going to move on to the next section, which I believe is 1.7 in your textbook. But I'm not really following sections in technically. I know what topics I want to cover. The precise definition of a limit. So you might say, we already know what a limit is. We already covered the definition. Well, not exactly. We covered a very fuzzy definition of a limit. And what we know about the limit, we know how to compute a lot of them, and we kind of know what it is. But we kind of know a limit as the y value you get close to when the x value is getting close to something. And that's kind of a problem, because what does it mean to get close? Right? That's where the vagueness comes in. What does it mean to be close? Different people might assume different things when you tell them the word close. How close are we talking here? Right? Within 2 decimal places, within 3 decimal places? Right? Does it have to be half a unit away, 1 unit away, 100 units away? Right? Some people have their own personal space, right? No, you're too close to me, don't talk so close to me. We're like, well, that's how I talk to all my other friends. No, that's too close for me, right? So the closeness can be a vague idea. So that is not good enough for math people. So you need to define exactly what close means. And in doing that, this is the idea they came up with to describe the closeness factor. And this is called the precise definition of a limit. So we say the limit as x approaches a of f of x is L and write the expression limit as x approaches a of f of x equals L if, okay, so here's the definition. Start to write some symbols here. For all epsilon greater than 0. So this upside down A, it's a mathematical symbol that means for all, for every, for each. So it's a universal quantifier. For all epsilon greater than 0, there will exist a delta greater than 0. I just told you that symbol already. There exists a delta greater than 0, such that if the distance between the x value and the a value is less than that delta, right? Possibly they're not the same. We don't have to be able to get to that x value. But as long as I can get my x close enough to a, how close? That close specifically. This is a number. Then the distance between f of x and L will be less than epsilon. And this is what we mean when we say the limit as x approaches a of f of x is equal to L. Right? So basically this is saying when the x values get close together, how close? Delta close. Right? The y values will get close together. How close? Epsilon close. Right? So literally anyone can come and they can tell you what close means to them, and this definition will fit their definition of close. It will not be vague. Everyone will be able to walk away with very specific numbers for their own purposes, and it should work out no matter what. In other words, someone should be able to come and tell you how close they want the y values to get. So for all epsilon greater than 0, someone is going to give you a tolerance. I want the y values to be this close. And you just have to show, okay, if you make the x values this close, then your y values will be that close, right? You can meet any tolerance that is given to you. As a picture, if you want to see a picture of what this is saying, basically. So let's say you have a function here, it's doing its thing, and you're focused on this point. Suppose that is your A. Now, for us, you kind of know that the limit L is going to end up being here, the y value. So what does it mean to say the limit is L? Well, someone can give you a tolerance, right? Open a window around L. And according to them, you need to be within that window to be close, right? And that one is going to be given. So it's going to go from L minus some tolerance to L plus some tolerance, right? So they give you a window. And when they say close to L, they mean within this window, right? So they can say, I give you a 2 decimal point leeway, right? So you can be 2 decimal points away from L in either direction. That's the window that I require. Now, different people will give you different size windows, but that shouldn't matter. The window can be anything. You should assume that it can be anything. So in other words, there's a window that you have to... Some people might let this window flow along the function, but I think you can get the idea here. We're kind of staying stationary. So there's a window here of where you want the y values to be able to be, right? So now you have to give them a window on the x that's going to meet that window. Now, if you give the window too wide, then you would have a problem. So for example, if you set the window here, you'll notice that there are y values on the function that's outside that window, right? So in theory, if you gave them this window, someone could say, no, that y value is not close enough. There's an output that's not close enough for what I want. So you have to be able to tell them a window that's going to work. So for example, you can give them this window, and you would notice that once you're within that window, just give another color, and you would actually create this window here. Notice that once your inputs are within this window, all your outputs would fit within that window, right? Versus a wider window, all your outputs will not fit. So in other words, someone can say, I want to get this close to the y value, and you need to tell them how close the x values have to get to be within that window. So you have to create a window that's going to be from a minus delta to a plus delta. Okay? So this window is given to you, and you need to find that window such that all your outputs live in the given window. So you need to show that you can meet any tolerance. So let me actually state that specifically, because conceptually that's easy. That's very important for you to understand when you're finding a limit by this way. I.e., given any epsilon greater than 0, tolerance for your y values. you need to find a delta greater than 0. So that the y values will be epsilon away from L. You should also note your delta may, or slash must, I mean if it's a constant then you should still think of it that way, depend on epsilon. So your delta might even be a function of epsilon. It might depend on the tolerance. So you basically saying, oh, the limit as x approaches 2 of x squared is 4. Basically what that is saying is that giving me a small enough window for the inputs, I can get close enough to 4 as close as you want. Right? So someone can say, what if I want to be 2 decimal places away? Okay, choose this window and you're fine. What if I want to be 100 decimal within 100 decimal places? Okay, choose this window. Right? Every time someone tells you a tolerance, you can respond to them with another tolerance, and that's your delta. Right? So the goal of these problems is you need to find a delta for any given epsilon. Do you kind of understand so far, or do you understand? Any questions about that idea? So we're basically saying when the x values get close to something, the y values will get close to something. And what does close means? Now we're putting values on how close. So someone's going to give you this value, and you have to figure out that value to make the closeness work out. And so whenever you're asked to prove a limit exists, or show a limit exists, or use the epsilon delta definition, this might be what it's called, via the epsilon delta definition of a limit. So whenever you're asked to prove a limit exists, show a limit exists, use the epsilon delta definition to show a limit exists, it means you have to use the definition that I have written down here. For every epsilon greater than 0, there exists a delta greater than 0 such that if x minus a is less than delta, then f of x minus L will be less than epsilon in absolute values, because we're doing a distance. So here's some 3 things I want, which we're going to do next time, but you can actually try to do them on your own first. See if you understand the definition here. So we're not going to do crazy problems here like we've been doing before, because the definition can be quite difficult to apply in certain cases, and you don't have to even make the function too difficult to do that. Like even just this one, it's probably more complicated than you think to prove that. Right? This is easier to prove than that, and that's crazy. So for Calc 1, we're going to keep the examples relatively simple. But if you ever, for those of you who are math majors and you ever take a class like Advanced Calculus, which is like a watered down version of real analysis, probably your first couple weeks will be spent just applying this definition and really understanding what it means and applying it to sequences and series and things like that. Which is why there are these cheesy math jokes out there where they go something like, oh, a mathematician and his wife are arguing and she's like, prove to me that you love me. And he's like, okay, fine, let epsilon be greater than 0. And most people won't, what the hell are you talking about? But everyone who saw the limit definition, they'll know, oh, he's starting a proof. Right, so it's a very famous way to start a proof. Let epsilon greater than 0 be given. Right? And it's one of the first ways new mathematicians, the day they became a mathematician, was the day they understood that proof. Ah, I let epsilon be greater than 0. Okay, so we're actually going to use that definition to prove these next time. You can take a shot at a couple of them, see if you can actually work it into the definition. And we'll show that tomorrow.
Did you find the property number?
No.